In this lecture, we'll discuss two real batteries. The first is the lead-acid battery that's in a car, and the second is an alkaline cell that you'd find in a normal disposable battery. Here are the reactions for the lead-acid cell. Now what we're going to do is figure out which of these is the anode and which is the cathode, and use oxidation numbers to figure out how many electrons are transferred for those two reactions. Pause the video now and figure out what the oxidation numbers for lead is in both of these reactions, and use that to figure out which is the cathode, which is the anode, and how many electrons are transferred in each half cell. So we can see that we have lead 0 on the left, and we have lead +2. We know the sulfate ion's -2, so the lead must be +2. So it looks like we oxidized the lead, and then it lost 2 electrons. If we look at the bottom reaction, we had lead 4, and we went to lead 2, so it looks like we gained 2 electrons. Let's put that 2 electrons. So we can see that we have our anode on the top reaction and our cathode reaction on the bottom. Okay, so I put in a few extra things to balance the reactions. I suggest that you take this reaction and balance it as an exercise. All right, let's look at the net reaction. And our goal is going to be to see how the voltage of this battery changes over time as the reaction takes place. So we can see we're going to combine these reactions and then cancel the things that are the same on both sides. All right, once we put these together, we can see there's a few things we can cancel out. We've got 2 electrons being generated and 2 electrons being used, and so that's going to cancel. And so if it's in a properly balanced redox, that should always cancel, of course. And we have hydrogen on both sides, so let's get rid of this one, and that's going to subtract 1 from here, so we'll have a 2 over here. Now it looks like that's as simple as we can get it. Let's rewrite this reaction on the next page, and let's include physical states, because we're going to need that for Q to see how the voltage will change over time. Okay, so we can see the net effect is that we're going to be oxidizing lead, reducing lead 4 oxide, in both cases making lead sulfate, and we're generating some water and getting rid of our electrolyte. So let's write Q for this. So you're going to need Q for the Nernst equation to see how the voltage varies with composition and hence with time. Take a few seconds, pause the video, and write out the expression for Q. Okay, so we see we've got a solvent, which we're only going to plug in as a 1 in our Q, and we've got a solid, which we plug in as 1 in our Q. So actually on top, we don't have anything except for a 1. On the bottom, what do we have? We have products over reactants. So reactants, we have a solid, going to plug in a 1, a solid, going to plug in a 1, and then we have a concentration of hydrogen sulfate. And we have to square that. And then we've got the concentration of hydrogen ion. And that has to be cubed. So there's our Q. So let's look at how that affects how the voltage varies over time. The voltage is going to be the standard voltage for this cell, which is about 2 volts, minus RT over NF log of Q. So we know, let's go ahead and write that this is about 2 volts. So this explains, by the way, why a fully charged car battery is around 12 volts, because you have 6 of these cells in a car battery. Okay, so what happens to the voltage over time? Let's write Q as a function of T. We know over time we're going to create more products, and we're going to use up our reactants. So I want you to pause for a second and think about what's going to happen with Q over time. If it's going to go up, if it's going to go down, if it's going to stay the same. Pause the video and write down your answer. Okay, well, we can look at the Q value here, and we can see that over time we're going to be decreasing the concentration of hydrogen sulfate and of hydrogen ion because they're reactants. We're going to be using them up. So this is going to get smaller and smaller, and so Q is going to get bigger and bigger. So Q is going to go up over time. And if Q gets bigger, this logarithm is going to get bigger, and that's going to start eating away at this. So we can see that the voltage is going to go down. Now, why is that okay for a car battery? Think about how long your car battery runs for. You use your car battery when you start your car, and that takes about a second. And then as you drive off, your alternator starts charging your battery again. So you never use a car battery for an extended period of time. So it's perfectly suited for this application because the fact that if you left it on, you would begin to drain it doesn't matter because it's never used continuously. Here are the two reactions for an alkaline cell. This is what we'd use in a normal long-lasting battery. So a disposable battery like a Duracell or something. Anyway, so looking at this battery, let's see if we can figure out, here's the two half reactions. I haven't completed them with electrons yet. So I want you to take a second to figure out which is the cathode reaction and which is the anode reaction, and how many electrons are being transferred. Take a few seconds to do that. Please pause the video. Okay, so we can see we have zinc 0 here going to zinc +2, so it looks like the zinc lost 2 electrons. And so we must have our anode up here, which means we must have something being reduced here. If we look at our manganese, we've got manganese 4, and over here we've got, let's see, this is +6 divided by 2, so this is going to be +3. So we went from manganese 4 to manganese 3, so we're reduced. And notice that there's 2 manganese atoms, so that's a reduction of 2 electrons. Okay, so we've got our cathode reaction. Excellent. Let's put them together, figure out what Q is, and then we can see how the voltage of this cell will vary versus time. We can see there's several things we can cancel. Let's go ahead and cancel those. We can see there's electrons being generated and used up. We've got 2 moles of base on both sides, and we have water on both sides. All right, let's write this including the physical states. So we have our net reaction written with physical states. At this point, I'd like you to pause the video and write down your prediction for how the voltage of this cell will change over time as the battery is being used. So we can see that since all the products and reactants are solids, Q for this is going to be equal to 1. So if we plug Q of 1 into the Nernst equation, we're taking the logarithm of 1, we get a 0, which means the potential is always equal to the standard potential. So in theory, if we graph the voltage as a function of time, the potential of the cell should be constant until one or more of the reactants are used up, and then it should just drop to 0. This is an ideal voltage profile for a battery that's going to have a long-term usage. In reality, little flaws develop inside the battery, and so that increases the internal resistance over time. And so there's a slight decrease, and then it rapidly decreases at the end as the battery breaks down completely. But nevertheless, it's approximately flat for many, many hours of usage. This is why alkaline batteries are very good for things where we need to have hours of usage as a time.